In 1818, a translated architectural survey circulated quietly among several European scientific societies. It documented a phenomenon that investigators could not easily explain. Across multiple ancient cities, interior environments appeared unusually stable. Temperatures remained moderated despite extreme external conditions. Heat softened in arid regions, cold diminished in northern latitudes. The survey offered no mechanism. Instead, the effects were attributed to thick walls, favorable orientation, or coincidence, and the observations were filed without further inquiry. What drew my attention was that similar descriptions appeared in unrelated records: underground chambers described as cool throughout the year, enclosed courtyards channeling air with measurable consistency, stone cities that resisted both heat and cold without fuel, chimneys, or mechanical systems. These were not isolated buildings, they were complete urban environments. Today, fragments of these designs still function unintentionally, noted during restorations or energy studies, yet rarely investigated as deliberate systems. If entire cities once regulated climate without combustion or electricity, their disappearance carries implications beyond architecture. The question is not simply how these environments worked, but why they were quietly deactivated after events that left little trace, yet changed how cities were meant to live. The accepted explanation for ancient climate management is conservative and consistent. According to architectural history, pre-industrial societies adapted passively to their environments. Builders oriented structures toward prevailing winds, thickened walls for insulation, and selected materials based on availability rather than engineering ambition. Temperature regulation, in this view, was incidental rather than intentional. I examined how this explanation appears in academic literature. Ancient cities are described as reactive systems. Heat was mitigated through shade. Cold was reduced through compact layouts. Courtyards are interpreted as social spaces rather than environmental regulators. Subterranean rooms are framed as storage rather than thermal buffers. This narrative rests on a key assumption: that ancient builders lacked the knowledge or motivation to engineer climate deliberately at scale. Any apparent regulation is explained as a byproduct of mass, geometry, or tradition. The idea of coordinated environmental control is generally reserved for modern times. The official explanation also emphasizes limitation. Without mechanical ventilation, active cooling, or combustion-based heating, climate management is assumed to be crude. Complexity is downplayed. Precision is considered accidental. I noticed that this framework simplifies interpretation. It allows scholars to explain diverse environments using the same logic. Thick stone equals insulation, height equals airflow, depth equals cooling. The model is elegant, but it depends heavily on generalization. What the official explanation rarely addresses is consistency. Passive adaptation should produce varied outcomes depending on region, culture, and material. Yet in many ancient cities, environmental behavior appears surprisingly uniform. Spaces separated by geography and culture exhibit similar thermal performance. The narrative also relies on absence. Because written documentation describing climate systems is rare, the systems themselves are assumed not to exist. Architectural features are interpreted symbolically or socially rather than mechanically. This approach is not unreasonable. Archaeology depends on caution, but it creates a blind spot. When features perform consistently yet lack textual explanation, they are often stripped of function and reassigned meaning. As I moved deeper into architectural records, I began to encounter environments whose behavior exceeded what passive adaptation alone would predict. Temperature stability persisted where mass and shade should not suffice. Airflow appeared directional rather than incidental. The official explanation accommodates these cases by isolating them. Exceptional buildings are treated as curiosities. Urban scale is rarely considered. That limitation becomes more apparent when examining the first contradictions, spaces where environmental control appears precise rather than approximate. The first contradictions emerged when I began comparing internal temperature records across ancient structures. Some underground chambers remained cool year-round, even in regions where ground temperature alone could not account for the effect. Others retained warmth in cold climates without evidence of sustained combustion. Airflow patterns presented a similar challenge. In multiple sites, I examined shafts and passages that produced consistent circulation. Smoke tests conducted during modern studies showed directional movement rather than random convection. These results were often noted but rarely explored. Humidity control raised further questions. Certain stone chambers resisted condensation despite temperature differentials that should have produced moisture accumulation. Drainage alone does not explain this stability. The evidence suggests controlled airflow rather than sealed isolation. Courtyards proved especially revealing. Officially interpreted as social or ceremonial spaces, many exhibited proportional relationships that optimized air movement. Narrow openings accelerated wind. Elevated exits drew warm air upward. These relationships repeated across cities with no documented contact. What struck me was the precision. Passive design produces rough mitigation. These environments behaved predictably. Temperature shifts followed patterns. Air moved where it was needed. I searched for alternative explanations. Could later modifications have altered performance? In some cases, yes, but in others, performance degraded only after modern restoration blocked passages or filled channels. The official explanation does not fully account for this degradation. If these features were incidental, altering them should not significantly affect environmental behavior. Yet blocking a shaft often disrupted airflow entirely. This raises a question. Were these features designed to work together rather than independently? The contradiction deepens when scale is considered. A single building might exhibit unusual behavior by chance. An entire district behaving similarly suggests coordination. At this stage, the evidence does not demand an alternative conclusion, but it does challenge the sufficiency of passive explanation alone. When design produces repeatable environmental outcomes, intention must at least be considered. That consideration becomes unavoidable when the same features appear across distant cities with similar results. As I expanded the scope of comparison, repetition became impossible to ignore. Ventilation shafts appeared with similar proportions in cities separated by climate and culture. Subterranean corridors followed comparable gradients. Courtyard layouts repeated geometric ratios. These features were not identical, but they were functionally consistent. Air entered low, heat exited high, thermal mass absorbed extremes, water interacted with stone to moderate temperature. I examined sites in arid, temperate, and cold regions. Despite environmental differences, the same architectural logic appeared. This suggests adaptation of a system rather than invention from scratch. The official explanation often attributes this repetition to convergent evolution. Similar problems yield similar solutions. While plausible, convergence typically produces variation. Here, variation was constrained. In several cases, later builders preserved these features without understanding them. Vent shafts were retained but disconnected. Courtyards were built over. Subterranean networks were sealed. I noticed that performance declined after these alterations. Buildings that once moderated temperature became uncomfortable. Later occupants compensated with fires, braziers, or eventually mechanical systems. This pattern suggests inheritance rather than innovation. Systems were maintained until disrupted, not reinvented. Mapping these features across cities revealed another detail. They often aligned with broader urban layouts. Streets, building orientation, and open spaces worked together. This coordination implies planning beyond individual structures. At this point, the investigation shifted from architecture to systems. Individual features could be dismissed, repetition could not. If these elements formed part of a coordinated approach, then climate control was not incidental, it was infrastructural. Understanding how such systems functioned requires examining them not as buildings, but as urban mechanisms. This chapter forms the core of the investigation because it reframes ancient cities as integrated environmental systems rather than collections of passive structures. When I examined these cities as wholes, a pattern emerged. Airflow was guided through streets, courtyards, and interior spaces in sequence. Heat moved predictably. Cool zones were distributed intentionally. Thermal mass played a central role. Stone absorbed heat during the day and released it slowly at night. But absorption alone does not regulate distribution. That requires movement. Ventilation shafts connected subterranean spaces to rooftops. Differences in pressure created circulation without mechanical force. Water features amplified cooling through evaporation. Importantly, these systems worked across districts. A single building did not operate independently. Courtyards fed adjacent structures. Subterranean networks extended beneath multiple blocks. Solar exposure was managed at scale. Building heights created shade corridors. Seasonal sun angles were considered. The city itself functioned as a regulator. The evidence suggests these systems were designed to minimize energy input. No fuel was required, no continuous labor. Once built, the system maintained itself. This does not imply advanced technology by modern standards. It implies sophisticated understanding of natural forces. What remains unclear is why such systems were abandoned. They were effective, they endured for centuries, yet at some point they ceased to function as intended. The systems were not destroyed in a single event, they were disrupted gradually. Shafts were blocked, channels were filled, layouts were altered. This suggests a shift in priorities rather than collapse. Climate control was no longer central to urban planning. Understanding why requires examining what happened when these systems fell out of use. The disappearance of ancient climate systems appears procedural rather than catastrophic. I examined renovation records, restoration reports, and occupation period plans. The language is consistent. Passages were filled, openings were sealed, spaces were repurposed. Functional elements were reclassified. Ventilation shafts became symbolic towers. Water channels became decorative features. Subterranean spaces became storage. This reclassification had consequences. Once a feature lost its function in documentation, it lost protection. Blocking a shaft no longer mattered if it was not recognized as operational. Over time, the system fragmented. Individual elements survived, but their connections did not. This process does not require intentional suppression. It emerges naturally when knowledge is lost. New builders inherit structures without understanding their purpose. They adapt them to immediate needs. As fuel-based heating became common, passive systems became redundant. Fires replaced airflow. Combustion replaced circulation. The architectural language changed. Thick walls were celebrated. Open systems were seen as inefficient. Eventually, the original logic faded. What remained were ruins and partial functions. By the time modern scholars encountered these features, their context was gone. Without that context, interpretation defaulted to symbolism or coincidence. This loss of understanding created architectural amnesia. Systems survived physically, but not conceptually. That amnesia persists today. In recent decades, sustainability research has reopened questions once considered settled. Architects now study ancient buildings for passive climate solutions. In doing so, they rediscover features long dismissed as incidental. During restorations, blocked shafts are reopened, airflow returns, temperature stabilizes. These effects are noted with surprise. Modern engineers replicate similar systems using computational models. What ancient cities achieved through form, modern design achieves through simulation. This comparison raises questions rather than answers. If these systems were effective, why were they abandoned? If they were known, why were they forgotten? The evidence suggests a shift in urban philosophy rather than capability. Energy became abundant, efficiency became secondary. What remains uncertain is whether this knowledge was lost accidentally or sidelined deliberately. The record is silent. As cities continue to excavate and restore, fragments of these systems reappear. Each fragment invites reconsideration. I do not claim a forgotten civilization. I do not assert hidden technology. The evidence suggests something quieter, that ancient cities once functioned as environmental machines and that this knowledge faded when priorities changed. What matters is not certainty, but awareness. The past may not be as passive as we assume, and the future may benefit from asking why systems that once worked were allowed to fall silent. The question remains open.